Welcome to this online training about the Intel FPGA Power and Thermal Calculator for Intel FPGA devices. My name is Steve. This training is available for desktop viewing, as well as in a format compatible with portable devices, both available from the same link included in your registration email. For either version, while watching the training, use the controls at the bottom and side of the screen to navigate to any point. Feel free to pause the training at any time to experiment with the software. When you are done with the training, please use the link provided in the registration email you were sent to provide us feedback on the training and ways in which it can be improved. I'll remind you about that later. This training focuses on the basics of power analysis and the use of the Power and Thermal Calculator, or PTC. By the end, you'll understand what is meant by static power and dynamic power usage. You'll learn how the PTC is used to analyze both. The PTC is your main tool for performing a quick analysis of power usage at any stage of a design. You'll learn how to set up and use the tool to do this. You'll also see how the tool can be used to calculate the thermal factors necessary for implementing a successful cooling solution for your design. The PTC takes into account the unique multi-die design of Intel Stratix 10 and Agilex devices to provide a complete solution for power and thermal analysis. Let's start with a look at power analysis in general with regard to FPGA designs. At a most basic level, what is power? Wikipedia provides a formal definition of power as the rate per unit time at which electrical energy is transferred by an electric circuit. The unit of power is the watt, which can be calculated at its most basic level as the current through a circuit multiplied by voltage, the electromotive force. All tools and analysis are based on this simple formula. Remember, power is as easy as pi. With that in mind, when we want to analyze and optimize power usage in today's high-performance FPGA designs, what are our biggest concerns and challenges? Increasing device densities and performance make power consumption considerations more important than ever. Today's larger devices can implement much more of a system's overall functionality, including many high-speed applications that were unheard of only a few years ago. With devices running at higher speeds and performing these more advanced functions, more power is required and consumed. There are many challenges regarding power when creating such a design. Early in the design flow, it's necessary to estimate system power usage to determine power supply and cooling requirements. This can be difficult to do, especially with an FPGA design that can change just by reprogramming the chip. Supply components must be considered along with the board space required to lay out those components. A cooling solution must be selected that must be robust enough to prevent thermal damage to components. With power supplies chosen, the design must stay within a fixed power budget. Going outside of this budget is not an option, since it could require redesigning the power supplies and cooling solution. At the same time, the system must meet a cost budget. Bigger power supplies and cooling hardware add to this cost. If power usage can be reduced, the overall system cost can be reduced as well. The system must also be reliable. The more fans and cooling hardware required, the more likely something could fail. Finally, the design cycle must be as short as possible. Development schedules are tighter than ever, and a lengthy design cycle just to meet power and thermal requirements is not acceptable. To meet these challenges, three main things are needed. First, you need to close on the design of the system power supplies and cooling solution as early as possible in the design cycle. This will help speed overall system closure. Next, you need to make sure that the design meets the power budget set for each power supply later in the design flow when the design is near or reaches completion. Finally, you need to be able to increase design efficiency and productivity to shorten the design cycle as much as possible. What tools can you use to meet all these needs? Intel FPGA provides the tools you need to close power in your system. At any point in the design cycle, use the Power and Thermal Calculator, or PTC, to model your power requirements and calculate what kind of cooling solution is required for your design. The PTC is an easy-to-use what-if analysis environment that can be used as a standalone tool or while using the Intel Quartus Prime software. With the information reported by the PTC, you can choose and start designing the system power supplies and cooling solution, meeting the need of fast system closure. Later in the FPGA design process, use the Power Analyzer built into the Intel Quartus Prime software to generate highly accurate estimates of power usage based on a design's actual resource usage, along with its placement and routing in the chip. This helps you meet the second need, meeting the power budget of the design. Finally, use the Power Optimization Advisor along with the automated power optimization options it suggests to automatically reduce power usage in your design. These recommendations and options are simple to implement, meeting the third need, increasing your overall design efficiency and productivity. To understand how a power analysis of an FPGA design works, you must first understand power usage in FPGA devices. When the device is first powered up and programmed with a design, the current usage ramps up until it reaches its static level of power usage. Static power is the current drawn by device resources that are not clocked by a user design. This includes leakage from all FPGA functional block resources. Static power excludes the DC bias power that gets consumed by the device's I/O pins and analog transceiver resources. This separate power usage is referred to as the device's standby power. Finally, when the device is in normal operation and the design is being clocked, dynamic power is added on to the overall device power usage. Dynamic power is the additional power used by the design as it is clocked. Dynamic power consumption, and therefore total power, varies greatly from design to design, but is based on operating frequency, resource utilization, and other factors. To understand how and when to use the power analysis tools, you must first understand power usage in FPGA devices over time, from initial power on to normal user mode. When the device is first powered up, the current usage ramps up, as shown here, until it reaches its static level of power usage before device configuration. Device configuration occurs at some point during the time labeled as static. In this diagram, the static section shows the power consumption of the device if no clock signal were applied. Clocks are held in reset during this period of time. Next, and most importantly, clocks are released and the device enters user mode. This is the normal operating power usage of the device. As mentioned, operating power usage is a combination of static power along with I/O and dynamic power. In this state, the system clock is oscillating and the design is operating. It's important to understand the differences between dynamic and static power. Once a design is complete, static power does not generally change with resource utilization. However, it is still affected by what operating modes are selected for particular resources and by I/O usage. Static power is also affected linearly by device selection and process variation, but exponentially by operating temperature. A device with more logic includes more transistors and thus will naturally use more static power. Be sure to check your selected device's datasheet for details on static power use. A device operating in a higher temperature environment without proper cooling raises junction temperatures and can greatly increase static power. An effective cooling solution can help with this. When designing power supplies, be sure to use the worst-case static power specifications for your selected device and operating environment. As mentioned, dynamic power varies from design to design. As such, dynamic power can be a more controllable power component to consider when creating a low-power FPGA design. The equation shown here illustrates this. Dynamic power is affected by the capacitive charging of transistors in the device, the momentary short circuit power that is expended when a transistor switches, the operating frequency of the design, and the number of flip-flops switching each clock cycle, referred to here as the circuit activity. Looking at the equation, the only factors a design can affect are the operating voltage, the operating frequency, and signal activity. The device can be run at a lower operating voltage, or the design could be run at a lower operating frequency, but reducing signal switching activity in a design is the single best way to reduce overall dynamic power. Signal activity, as it relates to dynamic power, is defined by two main factors. Toggle rate, defined as a percentage, refers to the average number of times a signal transitions in a second, or relative to a clock. Toggle rate can also be expressed in signal transitions per second. Toggle rate is typically less than 50%, since it is rare for signals in a design to toggle most or all of the time. However, extra factors, such as signal glitching, may cause an artificial increase in toggle rate. The toggle rate of a signal is the key factor in making an accurate estimation of dynamic power usage. Dynamic power increases linearly as the toggle rate increases. In the PTC, signal toggle rates default to 12.5%. This corresponds to the toggling of the output signals of a 16-bit counter. Static probability, defined as a fractional value between 0 and 1, refers to how much of a defined analysis period a signal remains at logic high. The analysis period is usually based on the duration that is needed for a test case to fully exercise the normal activity of the signal. At the extremes, a static probability of 0 indicates the signal is at ground for the entire duration of a test. Conversely, a 1 indicates the signal remains high for the duration. Static probability affects static power on I/O. For inputs, it affects the power usage of the logic and routing fed by the inputs. This is due to state-dependent leakage into the device. On outputs, resistively terminated I/O standards consume power depending on the level of the signal. Before continuing, it's important to understand a little bit about the unique architecture of Intel Stratix 10 and Agilex devices. While previous devices, like those in the Intel Aria 10 family, follow a more standard architectural design, Intel Stratix 10 and Agilex devices feature an advanced architecture, referred to as the Intel HyperFlex architecture. Intel Agilex devices featured the second generation of the Intel HyperFlex architecture, after it was first introduced in Intel Stratix 10 devices. A traditional FPGA architecture consists of several basic building blocks: memory, DSP, and logic array blocks, or labs, along with the routing wires that connect them together. Labs consist of adaptive logic modules, or ALMs, that allow you to build any type of logic function, along with registers for temporary data storage. A traditional FPGA includes thousands of available registers. However, the Intel HyperFlex architecture takes this further by including additional registers throughout the device's core fabric. The key building blocks for the architecture are bypassable hyperregisters located in every routing segment and at all block resource inputs. These hyperregisters, along with the traditional registers found in the ALMs, can either be included in a circuit path or bypassed selectively. With all these additional registers and the software tools to support their selection and inclusion in a design, the Intel HyperFlex architecture provides a fine-grained approach to the use of registers, because hyperregisters are essentially located everywhere throughout the core fabric. But what about the power used by all these additional registers? As far as static power is concerned, the hyperregisters are implemented as simple D flip-flops. Each one requires only a few transistors to implement, fewer than the number required to implement an ALM register, and much fewer than more complex resources like the RAM and DSP blocks. As a result, the hyperregisters collectively contribute minimally to the total static power, less than 1%. With regards to dynamic power, as with other resources, hyperregisters on their own do not cause an increase in power. During design optimization, the compiler takes register stages already implemented in ALM registers and replaces them with hyperregisters. As such, the signal activity has simply moved from the ALM registers to the hyperregisters. The use of the hyperregisters proves to be more efficient than using the ALM registers for optimization methods such as retiming and pipelining. Keep in mind, though, that through these optimizations, the hyperregisters do enable designs to run faster, and that increasing the clock speed of a design causes dynamic power consumption to scale with that increased frequency. Compared to Intel Stratix 10 devices, Intel Agilex devices' process technology also plays a part in reducing power. First, transistors are tuned for power based on their intended usage. For example, for device resources that don't require high performance, such as configuration blocks, the transistor leakage in those blocks is reduced. Second, a custom metal mix for manufacturing is used to reduce capacitance. Recall that in power calculations, such as the equation for dynamic power discussed earlier, power consumption is directly proportional to capacitance. So by reducing capacitance using this custom metal mix, the overall power consumption of the device is lowered. Finally, Intel Agilex devices use a 10 nanometer process technology. By moving to a smaller technology, the nominal voltage can be lowered, which lowers power. This, in conjunction with process tuning, enables lower power binning. In addition to changes in the manufacturing process, changes have also been made to the device itself to lower power use. The transistors and the number and type of routing channels were redesigned to reduce power. This includes new technology to reduce the leakage of the channels and leave unused channels floating. These changes help to reduce the dynamic power the routing in the device consumes. Intel Agilex FPGAs also have additional power management features that reduce power consumption. Power can be gated to unused resources, such as DSP blocks and memory blocks, including M20K blocks and the ESRAMs. M20K blocks also have their own lower power modes. Finally, unused transceiver tiles can be disabled or completely powered off. The final thing to think about before we look at the PTC is how will you power your Intel FPGA device? Traditionally, devices on a PCB are powered by supplies built from discrete components. Supplies like this typically require many parts that take up valuable real estate on your board. On top of that, more parts means more layout requirements that, if not followed, can lead to problems. Using separate components also means that noisy signals between parts can go into the board, causing issues in other parts of the design if not properly isolated. Finally, a discrete part power supply has a lower possible switching frequency because of the bulk capacitors required and their slower transient response. To solve these issues, you can build your FPGA power supply using one or more Intel Empyrean power SoC devices. Power SoCs combine the multiple components of a discrete part power supply into a very small package. By greatly reducing the part count, the supply requires less board space and has a simpler layout. No more internal noisy signals can get injected into the board. Intel Empyrean power SoC devices use all ceramic capacitors, so you get a higher switching frequency and a more efficient design. There are many available Intel Empyrean Power SoC solutions available. You can see some example package sizes and board arrangements here. The Intel FPGA Power and Thermal Calculator provides recommendations for the use of Power SoC devices based on the power requirements of your design. Learn more about Intel Empyrean Power SoC solutions at the link provided. Let's now take a look at the tools available for performing a power analysis on an Intel FPGA design. Now that we've defined the different types of power usage that must be analyzed, we can see how the Intel power analysis tools fit in. As mentioned, the PTC is a graphical tool that estimates power usage based on entered design information. As such, it can be used at any point in the design flow, though typically before or during early development. The accuracy of the PTC is reliable, but lower than the other tools. To calculate both dynamic and static power in the PTC, you enter known information about the design into the tool. For dynamic power, you provide estimated resource usage and clock toggling information. For static power, you provide information about the target device selected and the device cooling solution. The PTC can be downloaded as a standalone tool or as part of a full installation of the Intel Quartus Prime Pro Edition software. Other power analysis and optimization tools are found in the Intel Quartus Prime software. They are meant to be used on a design that is finished or nearly finished, but they can be used at any point once the design is compiled to provide power estimates as a guide for performing power optimization. The Intel Quartus Prime software Power Analyzer creates highly accurate power estimates that are based directly off the FPGA design. Static power analysis is performed using input values similar to the PTC. For dynamic power, exact resource usage is known from the fitter, and signal activity information can be provided directly as a user-entered toggle rate or through the results of a design simulation. Including simulation results provides a much more realistic picture of signal activity, making dynamic power estimates much more accurate. Note that the Intel Quartus Prime software does not support gate-level timing simulations for Intel Stratix 10 or Agilex devices. Finally, the Power Optimization Advisor not only provides recommendations for improving power usage, but it checks whether its recommendations are being followed. This includes compiler settings that reduce signal toggling to reduce dynamic power usage, and settings that adjust how many and what resources the compiler selects to reduce static power usage. This diagram illustrates the typical use of the available power analysis tools over the course of a project design cycle. Early in the design cycle, during the design concept stage, the PTC is used to start getting estimates of power based on information entered manually into the tool. Once the design is created in the Intel Quartus Prime software, a design profile can be generated and imported into the calculator, providing a more accurate early power estimate. During the main design phase, you can continue to use the PTC and more accurate design resource usage information to get good estimates of power at any point. Once the design successfully compiles, use the Power Analyzer to get more accurate estimates, now based on actual placement and routing results from the fitter. Finally, at or near design completion, simulation results can be provided to the tool to incorporate accurate signal toggle rates and static probabilities to get the most accurate estimate. You can continue to use the results from the PTC as a baseline for future designs. So just how accurate are the tool's estimates? How confident can you be with the results in making power-related decisions, such as the design of your power supplies? Power estimates are only as good as the power models used to describe a device's power usage. To that end, Intel uses a rigorous modeling methodology where detailed circuit models are created using HSpice. All models are then tested and calibrated against the actual device silicon. To further guarantee the accuracy of the models, power estimates are performed on the models using a variety of actual user designs. Even with highly accurate power models, the power estimates provided by the tools are only as good as the information that is provided to them. For example, are toggle rates accurate? Does the signal activity information model real-world operation of the design? Is the count of resource usage, such as the number of logic elements used, accurate for the design? The more accurate the information, the more accurate the estimates. 3 power model types are available, depending on the target device selected. Advanced and preliminary models allow you to perform an early power analysis on devices that may not be available yet for purchase, but are available for starting a design in the Intel Quartus Prime software. Advanced models are the earliest models available based only on simulation results. Preliminary models used post-layout simulation results along with correlation with actual silicon. Both advanced and preliminary models are subject to change after further characterization. Final power models will provide the most accurate results since they are tested and correlated with final silicon and actual designs. These models are not expected to change in future versions of the software. The Intel FPGA Power and Thermal Calculator always indicates the stage of the power model for the targeted device. If you are using a device that has a final power model, the PTC is expected to provide results within 15% of what you would see for the highest power rails on a real device on a board. This accuracy assumes accurate design inputs have been provided to the tool. The report generated by the tool will include recommended margins for designing your power and cooling solution, taking this accuracy into account. For the power analyzer, the results are expected to be within 10%, again assuming accurate information has been provided. To learn more about setting up and using the power analyzer, see the online training linked here. Now let's take a look at how to use the PTC to perform an early power estimate of a design. The PTC allows you to perform early estimates of power even before a project or any design files have been created. If a project is available, accurate information from the project itself can be exported from the Intel Quartus Prime software and imported into the calculator to save time when entering resource usage information. This also provides a more accurate power analysis since the information comes from the design itself instead of your own estimates. The PTC also provides information about device thermal management and cooling solution requirements based on a selected maximum desired junction temperature. The PTC can be directly launched from version 19.4 or later of the Pro Edition of the Intel Quartus Prime software, or run as a standalone Windows or Linux application, avoiding the need for an installation of the Intel Quartus Prime software. You can download the standalone PTC from the Intel FPGA Download Center as indicated here. As of version 20.3, no additional licensing is required to use the PTC with either Intel Stratix 10 or Agilex devices. The PTC is easy to use. Enter into the tool as much of the listed information as you can. You can enter in information manually based on your specific requirements and estimated resource usage, or through a file generated from the Intel Quartus Prime software. The more accurate and complete the information, the more accurate the power estimates will be for your final design. As information is entered, report information is generated that provides estimated power consumption for the device and the design. The calculated information is organized to provide power usage for each type of device resource and power requirements for each supply. As changes are made to the input data, the calculated values update on the fly, providing a true what-if analysis. The file types listed here are used with the PTC. First, a .ptc file is the main file type used to store all the settings input into the tool and all calculated results based on those inputs. Use it for backing up the information you've entered into the tool and for moving that information into a different version of the tool if necessary. As mentioned, you can generate a file from an Intel Quartus Prime project that provides detailed, accurate resource usage information for the PTC. This file type has the extension .qptc. Finally, the PTC supports importing resource usage information from a .csv spreadsheet formatted file. Older versions of the Intel Quartus Prime software and the older early power estimator tool generate this file type. To get started using the Intel FPGA Power and Thermal Calculator, open the standalone version of the tool or access it from the Tools menu in the Intel Quartus Prime software, as mentioned earlier. When you start the tool, you can either open an existing .ptc file or start a new analysis by selecting the appropriate device family. If you select a .ptc file, the device family will be selected for you based on the information in the file, but you can override the family selection to analyze power usage in a different device family with the same resource usage information defined in the file. If you enable the override, select the device family to use for the analysis. If you open the calculator from an open Intel Quartus Prime project, the targeted device family in the project is selected, and basic information about the targeted device will be filled in automatically. Prior to version 20.3, the PTC consisted of multiple tabs where you could enter information pertaining to your design and view output generated by the tool. Here is what the tool looked like. The rest of this training will focus on version 20.3 and later, but even if you are using an older version of the tool, the process for using it is basically the same. Here is what the calculator looks like in version 20.3 and later. The main difference from the older versions is that the resource usage tabs are now separate pages selected from the indicated page selection list. To use the tool, first specify basic information about the target device and how it will operate here on the main page, using pop-up lists as needed. This information includes the selected part number and the device grade. If you want to perform just a power analysis on the device without a detailed thermal analysis, you can also specify a fixed junction temperature. Once the main page is complete, go to each of the other resource information pages and enter as much information as possible about the different resources used in the design. On each page, discussed in detail later, specify logic resource usage, including ALMs and flip-flops, RAM and DSP blocks, clock domain properties and used PLLs, I/O and I/O-related IP cores, and transceiver block use and configuration. You can also specify CPU core usage when using a device variant that includes the hard processor system. You can enter information into any white or light gray text input fields. Grayed out input fields indicate fixed or single value input fields that cannot be edited. Dark gray fields and reporting windows, such as the power summary window, indicate output values calculated by the tool. When you have finished entering all the information about your design, switch to the report page to view a per rail power estimate. The Intel FPGA Power and Thermal Calculator can provide a detailed thermal report that accounts for the supported device family's multi-die architecture. Previous devices used only a single monolithic die, where heat was equally distributed and left the device uniformly. As such, there was only a single junction temperature that defined the device's thermals. Because Intel Stratix 10 and Agilex devices have multiple dies for the transceivers and, in some cases, high bandwidth memory, there is a non-uniform distribution of power and heat. Each silicon die has its own power usage and thus also has its own junction temperature. The different die areas cause heat to leave each die at a different rate. Thus, thermal management in these devices must ensure that each of these dies are below the specified operating temperature, and the overall thermals are defined by which silicon die heats up first. This advanced model uses a new thermal modeling term called SciJC. SciJC is best used to describe thermals for multi-die implementations that have a non-uniform distribution. SciJC is a dynamic value that is dependent on the application power and is influenced by multiple silicon dies. As such, multiple values are possible. The Intel FPGA Power and Thermal Calculator reports SciJC values for each die based on the design implemented in the device and the effect of multiple dies. The report provides a breakdown of power between the transceiver tiles and the core die. The tool calculates SciJC specific to your design. A SciCA value is also reported as a goal for the design of your cooling solution. SciCA defines the total cooling solution required to keep the device's junction temperature at or below the maximum operating temperature of the device. You can use these values reported by the tool to easily experiment with different transceiver settings and placement to reduce power usage and simplify the cooling solution. To learn more about thermal management and how the older early power estimator and now the newer PTC can help in designing a cooling solution, see the separate Intel Stratix 10 thermal management online training linked here. The basic thermal management factors discussed in this separate training are applicable to all devices supported by the PTC. The PTC should be your first main tool for performing a power analysis. As mentioned earlier, you can use the PTC at any point during the design flow. Let's look at how the PTC is used at three main phases of a design: before starting the design, during the creation of the design, and after the design is complete. Before even starting a design, you can use the PTC to get power estimates based on what you think will be in your design. The reported results are averages based on the input information you provide. You can easily play around with the information you enter into the tool to get a true what-if analysis for your future design. Again, the power numbers you'll get are only as accurate as the information you provide, so at this stage of the design process, use the output from the PTC as good ballpark figures to get started in designing your power and cooling solution. To continue adjusting the input information you've provided and to back up what you've done, save the current state of the calculator as a .ptc file. Any information entered into the PTC can be saved as a .ptc file. You can back up this file if you plan on making changes in the PTC, or you can save a new .ptc file from the tool. Making a backup like this is helpful if you want to experiment with making a change in the tool that could affect the entire power analysis, such as a change in device. Create the .ptc file, make the change, and then open the backup.ptc file if you don't like the results. Creating a .ptc file is also useful for easy sharing of PTC results. Share a .ptc file, and any user can open the file in the same version or a newer version of the tool. To continue a previous calculation, simply open a .ptc file from the File menu. A new instance of the PTC will open with the information from the .ptc file filled in. Be sure to review any warnings that may appear, especially when moving to a newer version of the tool. You can edit the information entered from the .ptc file and overwrite the existing file or create a new file with your changes. The second phase for using the PTC is while you're actually creating the design. As before, you can still manually add information about your design to the tool at this point, but you can also import design information directly from the Intel Quartus Prime software. This simplifies the process of entering information into the tool and provides a more accurate power estimate because the numbers will be based on your actual design. You can still add, change, or remove resource information from the PTC as you like after the import to see the effect on your design's power usage. Note that if you experiment with a major change to your design in the PTC, such as a change in device family or using a different device package, you should add margin to the PTC results. The PTC will still be analyzing based on the resource usage from before the major change was made, so the reported numbers will be less accurate. At some point, you'll want to make the same major change in the Intel Quartus Prime project, recompile the design, and import the updated design information into the PTC. Project resource usage is provided to the PTC using a .qptc file. To generate a .qptc file, either add the assignment shown to your project's .qsf file or enable the option in the Power Analyzer settings as shown. Once the option is enabled, the project must be completely compiled and the Power Analyzer run to generate the file. You can run the Power Analyzer manually or enable an option in the project settings to run the Power Analyzer automatically during a full compilation. To learn more about configuring and using the Power Analyzer, see the separate online training linked to earlier. To use the .qptc file in the PTC, simply open it in the tool. Note that you should do this before manually entering or editing information in the tool, since the information in the .qptc file overwrites everything already in the running instance of the calculator. Once you've imported the .qptc file, you can manually add to or adjust any of the imported resource usage information. Whether you adjust the .qptc information or not, save the PTC settings and analysis as a new .ptc file for future use. If you are thinking about moving a design from an Intel Stratix 10 device to an Intel Agilex device, you can import a .qptc file from an Intel Stratix 10 instance of the PTC and import it into an Intel Agilex instance of the tool. Simply open the Intel Stratix 10 .qptc file with an Intel Agilex device selected in the tool. Note that you cannot take an Intel Agilex .qptc file and import it for analysis on an Intel Stratix 10 device. The Intel Stratix 10 PTC supports the use of older .csv formatted files that were generated by version 19.4 of the Intel Quartus Prime software and the Intel Stratix 10 Early Power Estimator, or EPE. Once again, simply open the .csv file in the tool, add to or edit the resource usage settings as desired, and save as a .ptc file. The final design phase for using the PTC is when your design is complete. Even when you are finished with your design, you can still use the PTC to compare the design's actual power usage with the tool's estimates. You can also use the results as a baseline for future designs, making adjustments in the PTC to meet the needs of that future design. Again, to do this, simply import a .qptc file generated from the completed design project. This will be the most accurate representation of the resources used. However, note that only toggle information provided as assignments in the project will be included in the analysis. Of course, once the design is complete, use the Power Analyzer instead of the PTC to get the most accurate analysis for the current design. Here is a summary of the use of the PTC at the 3 design stages just mentioned. Again, the further along in the design, the better and more accurate the analysis will be. But there's no reason not to make use of the tool no matter how far along you are in your design. Now let's take a brief look at each of the pages in the PTC and some key inputs that should be provided to get the most accurate power analysis. Let's start with the logic page. Like the main page, information is entered into the white or light gray cells. On this tab, each row represents a design module, allowing for a breakdown of resource usage and toggle rate for each part of the design. Optionally, enter design module names to indicate the estimated or actual number of logic resources used by that part of the design. For the resources themselves, enter in the total number of registers, along with twice the number of ALMs used by the module. Half ALMs are used because two separate functions may be placed into a single ALM. If the design has already been compiled and you didn't import a .qptc file, you can find these values in the Place Stage section of the FITR report in the compilation report under Resource Usage Summary. Enter a clocking frequency and toggle rate for the logic. As mentioned earlier, a default toggle rate of 12.5% is set for all design resources. Finally, you can experiment with a higher or lower routing metric value instead of the default of 3. The selection of a routing metric is based on fan-out and the amount of routing resources used. A higher value represents more routing resource power usage. As input values are entered, output values in the dark gray cells update to provide routing and logic block power usage and resource utilization information for the design. Moving to the RAM page, rows represent design modules with all identically configured RAM. You can also use separate rows to describe a particular RAM module implemented with one or more RAM blocks. First, set the RAM type. If the design has been compiled, this can be found in the FITR RAM summary section of the FITR Place Stage report. Next, set the number of RAM blocks, the RAM data width, and the RAM depth. The number of blocks should be specified as the number of logical blocks that make up the RAM, not physical blocks. This is because more than one physical block may be used to implement a larger logical memory. Based on the number of logical blocks specified, the PTC can figure out what the minimum physical block usage would be, which corresponds to the amount of power used by the block resources. Specify how the memory is set up by choosing a RAM mode, and then enter the RAM clock frequency and enable signal active percentages. Dynamic power is consumed only when the memory is enabled and clocked, so power can be saved by occasionally disabling the entire memory or just the read or write functionality. Finally, the toggle percentage represents the toggle rate for the output signals of the memory. Like the RAM page, each row of the DSP page represents either a module where all DSP instances are configured the same, or a specific DSP inferred structure or IP. First, specify the DSP configuration. There are many options available. As usual, if the design is already compiled, check the compilation report to see how any used DSP blocks were configured if you're not sure. Next, set the number of instances to the number of DSP instances that all have the same configuration, clock frequency, toggle percentage, and register usage. Multiple instances can be implemented in a single DSP block, so this does not necessarily equal the number of DSP block resources used in the design. As with RAM, set the clock frequency, clock enable active percentage, and the output toggle rate. Enable the pre-adder and coefficient options as needed. Finally, set the number of registered stages for the DSP module. The value to use here depends on the selected configuration, so see the PTC user guide for details on what value to select. Rows on the clock page represent each clock network or separate clock domain in the design. Note that you do not need to specify what clocking resource is being used for a particular domain. While Intel Stratix 10 and Agilex devices have global, regional, and periphery clock networks, the PTC does not distinguish between them due to the minimal differences in each one's power usage. The fields on this tab are relatively self-explanatory. The clock network fanout can be obtained from the global and other fast signals summary report in the fitter place stage report. Like RAM and DSP, set the enable active percentages for each clock. Gating an entire clock network, or at least the local part of a clock network driving particular logic array blocks, can have a significant impact on dynamic power usage, since unclocked resources use little to no dynamic power. Finally, the utilization factor for a clock is similar to the routing metric value for logic. A higher utilization factor indicates that the clock is more spread out over the device and has a higher fanout. Again, you can stick with the default value of 2 or experiment with higher or lower values. As mentioned earlier, Intel Stratix 10 and Agilex devices feature hyperregisters throughout the architecture. When the PTC calculates register power usage, whether they are registers in the ALMs or hyperregisters, it analyzes both the toggling of the clock and data signals. For hyperregisters, data signal power is pretty much the same whether the hyperregister is enabled or bypassed. Since hyperregisters are mostly located in device routing, hyperregister power usage is lumped into the power usage of the routing where it is located. This is handled automatically by the tool. As such, the use of hyperregisters should not be included in the number of flip-flops column on the PTC's logic page. If you are using the PTC before creating a design, you would not know hyperregister resource use anyway, because the use of hyperregisters is determined late in the compilation process. For the power used by clocking hyperregisters, the separate clock page, as just discussed, is used. On the clock page, you can specify the total fanout for a particular clock domain. The higher the fanout, the more resources are being clocked, thus increasing dynamic power usage. As such, you can include hyperregister use in the total fanout column on the clock page. You can set this option accurately by getting the actual fanout number from the global and other fast signals summary report as mentioned. The PLL page is relatively self-explanatory as well. Each row represents one or more PLLs in the design with all the same properties. Set the PLL type to either a PLL driving the I/O banks or feeding the internal device fabric. Specify the number of PLL blocks, the number of counters, and the operating frequency. Note that some IP entered on the I/O IP page, discussed in a moment, might automatically fill in rows of the PLL page if the IP uses PLLs. Highlighted here, you can see that the DDR4 hard memory controller IP added 3 PLLs to the page. Next, specify the properties of I/O used in the design. Each row on this page represents one or more I/O pins that have all the same properties. Use the number of pins column to indicate how many pins a particular row is describing. For the application column, select whether the I/O is a GPIO or used as part of a SerDes. If the external memory interface IP is specified on the I/O IP page, the application column will default to EMIF as shown here. If the application is EMIF, the DDR rate column becomes available. Set this to match the clocking relationship between the external memory PHY and the internal user logic, which is also specified in the IP parameter settings for the external memory interface. Available values are full speed, half speed, and quarter speed. Next, specify all the basic properties of the I/O, such as direction, I/O standard, termination, and drive strength. Set the SDR/DDR column to single or double data rate, depending on whether the I/O can change state either once or twice per clock cycle. Toggle percentage represents the percentage of clock cycles where the I/O signal toggles, while OE percentage is the percentage of cycles where an output I/O is enabled or a bidirectional I/O is enabled when in output mode. The remaining settings include I/O clocking frequencies and settings specific to when the application is set to SerDes. Set these values as appropriate for your design. On the I/O IP page, each row represents an IP core in the design. Select the correct IP in the IP column. If an SoC variant of the device is used, hard processor system peripherals may be available here. Select them as appropriate. Other columns are used to describe the settings for that IP, such as the number of DQS groups for the external memory IP. Again, set values to match your design. As mentioned earlier, adding IP on this page automatically fills in rows on other pages, such as the PLL and I/O pages. Be sure to verify what's been added on the other pages when you add IP here. On the transceiver page, specify transceiver configuration and usage in your design. Some of the options available depend on the transceiver tile type you're using and the operation mode of the transceiver. E-tile transceivers are general-purpose transceivers, while P-tiles are for PCIe applications. Other tile options will be available depending on the device selected on the main page. If you're using an E-tile device, as shown here, you can specify the number of channels and the starting channel location on the tile. If the design allows it, spreading out transceiver channels on a tile can be an effective way of reducing thermal hotspots on the device. This can help simplify the device's cooling solution. We'll discuss this a bit later when we talk about thermal analysis, but for more details, see the thermal management training linked to at the end of this training. Also for E-tiles, you can estimate power usage when a transceiver is in normal or low power mode. Use normal power mode for thermal modeling and regulator sizing, since the board design should be based on maximum power usage. See the E-tile transceiver PHY user guide to learn how to switch a transceiver into low power mode. Specify if and how you are implementing FEC, the protocol for the Ethernet hard IP if applicable, and the data modulation mode. Finally, if you're using a P-tile device, select the appropriate PCIe protocol from the options available. The hard processor subsystem page is only used with an SoC device. Enable the HPS system switch option, select the number of CPU cores in use, and choose a benchmark application. The applications are meant to be representative of how hard the processor will be stressed. HPS peripherals may become available for power measurement on the I/O IP page, so be sure to go back to that page and choose the peripherals in use after enabling the HPS here. Finally, the High Bandwidth Memory, or HBM page, is configured for devices that include HBM memory stacks in the device package. Each row describes the power usage for each physical channel access to a die in an HBM stack. Select the memory stack and the physical channel used to access a particular die in the stack. Recall that each physical channel is divided into two pseudo channels. For each pseudo channel, select a traffic pattern that most closely matches how you expect to access the memory in your design. While resource-specific calculated power output numbers appear on each resource page, the easiest way to view calculated power numbers is with the Power Summary window and the Report page. The Power Summary window displays the power calculated on each of the resource pages and sums them together. This is a quick way of viewing overall power usage of the design. If you accidentally close the Power Summary window, you can reopen it from the PTC View menu. The Report page displays the power usage for each required power rail in the design. Each rail is broken down into 5 values. We'll look at these values in a moment. For each power rail, there is an option named Regulator Group. This option allows you to create regulator groups for building the supply for each rail. For Intel Stratix 10 devices, regulator groups can be set up automatically based on pin connection guidelines using an option selected at the top of the report. If this option is set to custom, specify a group number for a particular power rail. Rails with the same number become parts of the same regulator group. Regulator groups set up here on the report page correlate to groups on the Empyrean page, making it easy to design a power tree using Intel Empyrean Power SoC devices. We'll look at the Empyrean page in a moment. The 5 values reported for each power rail are described here. The first value is static current. This defines the total static power of the rail. As such, it does not rely on clock frequencies applied to the design and does not include standby power defined earlier. Next is dynamic current. For rails that supply power to resources that use dynamic power, this value sums up the power used by those resources on all calculator pages. Next is the total current before Smart VID savings. Smart Voltage ID, or Smart VID, is a feature available in select devices that allows the device to dynamically adjust its own core voltage down to a silicon-specific lower limit based on changes in the operating environment. This value shows what the total power usage would be using the typical core voltage of the device instead of the Smart VID reduced voltage. This way, you can see what the power swing would be between the typical voltage and the low voltage. The total current output is a calculation of the total power requirements for the rail, including the savings from Smart VID, if the feature is used. If Smart VID is not used or available, this value will equal the previous value. Finally, the recommended margin, if provided, can help in sizing the regulator for a power rail by calculating a margin based on the ratio between static and dynamic power required for that rail. Once you've grouped power supplies on the report page, you can organize those groups and how they feed each other on the Empyrean page. For each power regulator in your supply design, you'll specify the regulator's input voltage, output voltage, and type, such as switching or linear. To build up a power tree, specify if a regulator group is an intermediate supply or fed by a parent group. An intermediate supply is a regulator that supplies other regulators but does not power any rails for the FPGA. The parent group option indicates which other regulator group feeds the selected regulator. Let's look at an example of the Empyrean page. In this example, regulator groups numbered 5 and 6 have 12-volt inputs, but the parent group option for both is set to 0. That means these regulators are the start of the power tree. Regulator group 6 has the intermediate supply option enabled. This means that it drives other regulators, but does not drive any FPGA power rails directly. Group 1 has a parent group of 5, and groups 2 through 4 have a parent group of 6. This indicates that these regulators are fed by regulators 5 and 6, respectively, further correlated by the fact that group 5 has a 3-volt output and group 1 has a 3-volt input. Group 6 has a 5-volt output and groups 2 through 4 have a 5-volt input. The page provides a list of suggested Intel Empyrean parts to build this power tree, along with additional pin-compatible parts for some of the regulators, where an alternate part is available. This diagram illustrates the power tree from the example. As you can see, the PTC makes it easy to design the power regulators required for your design and point you to the parts you need to implement it. For the final section of this training, we'll look at how to set up and perform a thermal analysis using the PTC. As discussed, the PTC can perform a thermal analysis that accounts for the supported device's multi-die architectures, providing a breakdown of power between the transceiver tiles and the core die. The tool calculates psi-JC, the thermal resistance factor, for each die specific to your design. A psi-CA value is also reported as a goal for the design of your cooling solution. Remember that the higher the psi-CA value, the simpler the cooling solution you need to implement to meet the thermal requirements of the design. The PTC supports 4 different modes for thermal and associated power calculations. The default mode is to use a constant junction temperature for all dies, which essentially disables the multi-die thermal analysis. The second mode is probably the most common option. In this mode, set the ambient temperature around the device and specify TJ max, a maximum desired junction temperature for any of the dies in the device. The tool will calculate a psi-CA with the assumption that at least one of the device dies is at the specified TJ max. That means that the numbers provided can be used to create a cooling solution that will keep the junction temperature for any die at or below the specified value. The third mode is almost the opposite of the second mode. Specify a psi-CA value and the tool will calculate the maximum junction temperature expected for any of the dies with a cooling solution implemented with that value. The final mode calculates what the ambient temperature around the device will be when a cooling solution with the given psi-CA is used. You can switch the calculation mode at any time, and the tool will recalculate on the fly. The thermal analysis page is where options for the analysis are set and the calculated values are reported. For Intel Stratix 10 devices, the options and detailed reporting are enabled on the thermal analysis page by setting the power characteristics option on the main page to maximum as shown. The thermal analysis page is always active for Intel Agilex devices. To improve performance while working with the PTC, set the power characteristics to maximum only after entering in all your design information on the other resource usage pages. To get an accurate thermal analysis of your design, it is very important to accurately specify the properties of transceiver interfaces you will use. This is done on the transceiver page. Besides the basic settings such as operation mode, data rate, and voltage, you can also specify the transceiver tile type if multiple tile types are available on your targeted device, and the transceiver die where the interface will be located. The diagram on the left illustrates the placement and naming of the transceiver dies around the core die in a typical device. Once you've selected a die, specify the number of channels used by each interface along with the starting channel location. Dies may have 12 or 24 channels, as shown on the right, so the channels used for each interface on a particular die cannot overlap. Set the number of channels and starting channel location appropriately to avoid overlap. Providing die-specific transceiver use information is critical in performing an accurate multi-die thermal analysis. As you edit values in the PTC, make sure to look at the Warnings and Errors window in the tool to see if there are any errors with any of the settings you have selected, such as overlapping transceiver interfaces, before going to the thermal analysis page for the final results. Here's a closer look at the thermal analysis settings on the thermal analysis page. Depending on the calculation mode, different options to set are available on the right, such as the ambient temperature and TJ max. The PTC reports thermal values based off these settings, with the assumption that at least one of the device dies is at the specified TJ max. That means that the numbers provided can be used to create a cooling solution that will keep the junction temperature for any die at or below the specified value. Optionally, you can enable an added margin on the calculated values, currently fixed at 25%. Note that this margin only applies to the thermal values calculated on the thermal analysis page. The values on all other pages do not display this added margin. The final option is the TSD mode. This option, for Intel Stratix 10 devices only, enables temperature sensing diode, or TSD, offset calculations. Each die, including the core, includes a temperature sensing diode. However, the TSD may not be located exactly at the location of a temperature hotspot. Adding the offset to the value reported by the TSD for a particular die provides an accurate value for that die's junction temperature. You can choose to calculate this offset based on the on-chip digital thermal sensors, or DTS, or off-chip TSD components. Let's look at these TSD offsets in a little more detail. By adding the temperature sensor Intel FPGA IP to a design, you can read out the temperatures reported by each DTS on the core die and each of the transceiver dies. The heat map shown here illustrates how the sensors may not be located exactly at the hotspot on a particular die. With the TSD offset values calculated by the PTC, you can include them directly in your design so that readings from the sensors are accurate. However, note that these offsets and the other thermal calculations are unique for each design implementation. If any changes are made to the design, you would need to recalculate all the thermal parameters in the PTC, including the TSD offsets. Based on the values entered in all the pages of the tool, the thermal parameters discussed earlier are calculated and displayed on the thermal analysis page in the solution table. Here, you can see a breakdown of power usage and SiJC for each die, including the core and an HBM if available. A recommended SiCA is also displayed. In the example shown, transceiver tile 2.1 uses the most power, but tile 2.0 has the highest SiJC. The cooling solution should be designed to account for this, or the transceiver design and placement could be adjusted. For Intel Stratix 10 devices, the TSD offset calculations are also displayed here. The offset value represents the difference in temperature between the hotspot on the die and the location of the sensor itself. Adding the offset to the value reported by the TSD for a particular die provides an accurate value for that die's junction temperature. The solution table is used as a summary of the calculated thermal values, as well as what the values would be if the core junction temperature was 5 degrees above or 5 degrees below its calculated value. No temperatures in the solution table should exceed the values shown in the maximum junction row of the table. Note that even if the temperatures in the middle column do not exceed TJ max, at least one die may exceed TJ max in the plus 5 degrees column. As such, the plus 5 degrees column should only be used as an analysis metric and not as a basis for the cooling solution. The variance in core junction temperatures reported can also be used to create a temperature-dependent core die power curve. This is often used by computational fluid dynamics, or CFD tools, when analyzing airflow and cooling solutions. This concludes the training. For more information, we recommend the linked documents listed here. Start with the PTC User Guide for detailed information about all the settings and options available in the tool. The Intel Quartus Prime Software User Guide on Power Analysis and Optimization, and the Intel Agilex and Stratix 10 Power Management User Guides should be your go-to references for power management. The other listed documents provide detailed information about the power-saving features of other device families. 2 white papers provide more detail about how power analysis works in general. You can also learn more about Intel Empyrean Power SoCs at the Power Solutions website. You can find links to these documents and others at the Power Solutions Support Center on the Intel website. Intel FPGA provides many additional technical support resources besides technical training. Check out the online Intel FPGA forums. They're a great place to connect with other users to share experiences and find solutions to common issues. Use the knowledge base to find solutions to the most common issues you may run into. Manage your software licenses and online training registrations using the Self-Service Licensing Center. Finally, for local assistance, contact your local Intel FPGA sales office to speak with a field applications engineer. One more thing. When you registered for this online training, you should have received a link to a short survey where you can provide feedback. We'd greatly appreciate it if you'd fill out that survey now. We're constantly updating and improving our training materials, and your feedback helps us create the materials that you want. Thank you for your feedback. My name is Steve, and I want to thank you for taking this online training about the Intel FPGA Power and Thermal Calculator.